So today we'll start talk about the stability of a system. And as I told you before, that whenever you design a system, the first thing that comes into mind is to check the stability of the system, whether the system is stable or unstable. And thereafter we move towards the transient analysis or anything another sorts of performance measurement or study the performance behavior of the system. So this is one of the important parameter for assessing the performance of the system, because you talk about the response of the system, transient response of the system, or the steady state response of the system when your system comes out to be stable. But if it is not stable, then you don't go towards studying about the performance until you achieve a stable system. So after designing the system, the first task for the designer is to somehow make the system stable. Then the second task is to make the performance of the system achieve the desired values. So stability can be studied into two sub parts, one of which is called as absolute stability, the other is relative stability. So we first talk about this absolute stability. So this is the most important characteristic of any the dynamic behavior of control system, and this in fact tells about the system stability or instability. So when we say that system is stable, let's say we're given two systems and we say both of them are stable. By this we mean the system is absolutely stable, absolute stable. So normally this term absolute is dropped. So we informally say system to be stable. By this we mean that the system is absolute stable. So absolute stability is concerned with system stability or instability. Now if we talk about a linear time invariant system, it is said to be stable if the output eventually comes back to its equilibrium state when the system is subjected to an initial condition. So the system is said to be stable when the output comes back to equilibrium state, which means that, so this is something that we saw in the waveforms that we drew for stable and unstable systems. So we saw that the systems which are absolute stable, the systems which are stable will have their curves or the graphs attaining equilibrium or steady state after a certain period of time. And by initial condition, we mean that the system might be having some energy stored within the system. So this is what we refer to when we say initial conditions. This means that for analyzing whether the system is stable or not, it's enough that we provide the system with the energy that is stored within the system. For example, let's talk about an RLC network, which will be storing energy in the inductor and capacitance. So without providing any sort of input to this system, without connecting any voltage or current source to the system, we can simply short the circuit. So the circuit will then be operated by the energy which is stored within the system, and that is what we refer to by calling as initial conditions. So if by short circuiting that circuit, if the response, the output of the system does not deviates out of bound, or it comes back to an equilibrium state after short circuiting the circuit, we say that the system is stable. If anyhow by short circuiting the circuit we observe that the output goes beyond bound, or it uh, continuously or persistently goes out of the equilibrium state, then we say that the system is unstable. So initial conditions are the thing that will be, or in other words, you studied about force and natural response. So natural response arises from the parameters within the system, and thus the natural response is sufficient to tell you that the system is stable or unstable. An LTI system is said to be critically stable if oscillations of the output continue forever. So this is what I showed you in previous lectures that if you are going to have a persistent oscillations which are not neither decaying nor increasing, then such type of system is said to be critically stable. So you'll be having persistent oscillations without any sort of damping. And then a system is said to be unstable if the output diverges without bound from its equilibrium state when the system is subjected to an initial condition. So we are not talking about any sort of forced input or forced response of the system. We're talking about the natural response which arises due to initial conditions. So initial conditions are sufficient to state whether the system is stable or unstable without giving any sort of input from the outside. Now, if the system is subjected to bounded input, so we are talking about a stable system. If the system is subject to a bounded input or disturbance and the response is also bounded, then we say that the system is stable. For example, if you talk about the first figure, we provide this system with a bounded input. So this RT is the input given to the system. And if we are going to have a bounded output, so you see, you can observe that the output is reaching an equilibrium, a steady state after a certain period of time. So such type of system is a stable system. While if any system exhibits a response which does not have bound, which is not bounded. So if you are going to have a persistent increase in the output for a bounded input, then this system becomes an unstable system. So these are the waveforms that we studied in previous lectures, and we'll say that for what values or for what parameters of the system does the response become stable or unstable. The absolute stability of the system can be known by looking at its closed loop poles. If all the closed loop poles lie on left half of S-plane, then the system is absolute stable. So this is nothing new, and we have already studied about this, that if you're going to have all the poles lying on left half of the S-plane, then in that case the system is said to be stable or absolute stable. And if in case any pole lies on right half of a S-plane, for example, if you talk about a system having, let's say, uh, 5 poles or 10 poles, so any single pole out of these 5 or 10 poles, if that's that one pole is going to lie on right half of S plane, that will be sufficient or that will be enough to make the system unstable. So what do we mean by poles lying on left half of S plane? There is a note, includes poles on the j omega axis. So if you are going to have poles lying on j omega axis, which is going to make the system critically stable, then mathematically we say that the system is stable because poles on the j omega yields oscillations that neither decay nor grow. But practically, if you're going to have poles lying on the j omega axis, so I'll talk about the poles that will lie on j omega axis and how the response is going to be yielded. So practically, if you have poles lying on j omega axis for any system, then in that cases, the presence of noise may increase the amplitude of oscillations, which means that the oscillations which were bound or which were neither growing nor decaying, because of presence of noise will start increasing and go beyond bound and will make the system unstable. That is why practically we try to avoid having poles on the j omega axis, and we prefer having all the poles lying on left half of S plane in practical systems. And notice that we always talk about poles in the closed loop system. So these are the closed loop poles. The closed loop poles should lie on left half of the S plane. Now the second term that we have is relative stability. And for any closed loop system, for a closed loop stable system, the degree of stability can further be characterized, which is referred to as relative stability. So when we talk about a stable system or an absolute stable system, then the term relative stability arises. So relative stability is something that we are going to compare the stability of the system with another system or any reference. So it will be a sort of comparison between two or more systems, or it will be a sort of comparison of a stable system with a reference or a standard. So relative stability of systems uh, is something that we talk about when we compare two stable systems. So it's important that for all the systems for which relative stability is being studied for should be stable. For example, there exists a difference in the stability of, so there is a correction. It should be stability of a modern fighter aircraft and commercial transport. So if you talk about the uh, maneuver of modern aircraft and commercial transport, the more stable an aircraft, the more difficult it is to maneuver. Thus, one outcome of the relative instability of modern fighter aircraft. So, though the modern fighter aircraft will be stable, but it will be relatively unstable compared to the commercial transport or the aeroplanes that we move through. So these fighter aircraft, the outcome of the relative instability, the reason for this is that it should be having high maneuverability. This can be because in case of commercial aircraft, if you are going to have a high maneuver, then in that case it will be quite violent to the passengers, and that is why we try to keep the stability of modern fighter aircraft or the fighter aircraft less than the commercial aeroplanes. The relative stability can be measured by the relative real part of the roots. So if suppose that the roots of the characteristic equation or poles of the closed loop poles of the transfer function are located on S plane, and if suppose that there is a root R2 which is located at the left is located at the far left side of the S plane compared to R1. So if you look at this particular figure, in this case you are going to have the real part of R1 smaller than the real part of R2. So a root R2 is relatively more stable than R1 if real part of R2 is larger than R1. So we say that this the root R2 will be relatively more stabler than the performance that will be exhibited by the roots R1. The term relative stability is used in relation to comparative analysis of stability. So, which means that you will always talk about relative stability when you analyze two or more stable systems, and you want to compare the stability of these two or more systems. So, another term, another way of knowing the relative stability of system, another way of knowing the relative stability of any system is to study or analyze the behavior of the transient responses of the system. For example, the time domain specifications that we talked about in previous lectures, like if you have a system that exhibits more transitory nature compared to a system which is less transitory, then we say that the system which is less transitory is stabler, is relatively stabler than the one which is more transitory. So relative stability is concerned with the attributes of transient behavior. So the same attributes that we studied, like time domain specifications. And measures of relative stability are maximum overshoot, damping ratio, gain margin, phase margin. So we studied about maximum overshoot, the damping ratio, but gain margin, phase margin will be discussed in the next unit when we talk about Bode plot and Nyquist plots. Now this is what we concluded in the previous lectures and is again shown over here just to review that how we know whether the system is stable or not. And for the second order system, so how do we know whether the system is second order is by looking at the poles which are located on the S plane. So this is S plane, and since we have two poles which are located on the S plane, then we conclude that we are talking about a second order system. Had there been three poles, then it would have been a third order system. And likewise, as many number of poles you're going to have in the on the S plane, then the same order will the system will be having. So since if you're going to have the poles of the transfer function or the roots of the characteristic equation, and we're talking about the closed loop system, that lie on left half of S plane, then in that case you're going to have the output response corresponding to step input shown by this, and such type of system is absolute stable. Likewise, if you're going to have the poles located on the plane in this manner, so we say that they are uh, complex poles which exist for the system. If you are going to have complex poles in this manner, in that case you will be having a response which is underdamped as shown. But still you're going to have this oscillations die out, and this response will finally achieve a steady value, and thus the system is said to be absolute stable. And one thing here is to note that poles which are complex in form, they always exist in conjugate forms. For example, if you're going to have this particular pole as, let's say, 2 plus 2j, 2 plus j2. So if this pole is located in the S plane at this particular location, then the other pole will be having the value 2 minus j2. So complex poles always exist in conjugate form. This will always be happening in control systems. So if suppose that you're in the same system given a pole which is located, let's say, at location 5 plus 3j. So this particular pole will always be having its conjugate somewhere at 5 minus 3j, or in other words, complex poles will be having a mirror image about the real axis. So these two conditions are absolutely stable when you have poles lying on left half of S plane or they exist in complex conjugate form. While if you are going to have the poles lying on the j omega axis or the imaginary axis, so this is imaginary axis and this is real axis. If the poles are going to lie on the imaginary axis, in that case you're going to have persistent oscillations without any sort of damping like this, and such type of system is said to be critically stable. While if the poles lie on the right half of S plane in complex form, in that case you're going to have the waveform which will be sinusoid exponentially rising, and the system will become unstable because the output now becomes unbounded for a step input which is bounded. So for a bounded input you're going to have an unbounded output when the poles are lying on right half of S plane in complex conjugate form, and thus the system is unstable. And if you are going to have poles lying on the real axis on the right half of S plane like this, so in that case you're going to have exponentially rising output that will keep on rising indefinitely, and such system is also an unstable system. So now we conclude that any root lying on right half of S plane makes the system unstable. If one or more repeated roots are present on j omega axis, then the system will be unstable. So this is one more important thing to note, that if you are going to have repeated roots on the j omega axis, for example, shown over here are two poles of the transfer function. Had the transfer function, or if suppose that you were having a system of fourth order and all the four poles of the transfer function or the four roots of the characteristic equation lie on j omega axis, then in that case the system is going to be unstable, not critically stable, and that should be repeated. So there should be repeated roots on the j omega axis. So if you're going to have, for example, if this value is let's say minus 2.5j, and the other, sorry, plus 2.5j, and this is minus 2.5j, then again you have one more pair of roots again lying on the same point, plus 2.5j and minus 2.5j. So that means you're going to have repeated roots on the j omega axis, and that such type of system will be unstable. Now there are certain methods to determine stability of the system, so one of which we'll study in this unit. And the following are the methods employed to determine the stability of a control system. Routh-Hurwitz's criteria, which will be studied in the next lectures. And this is a sort of analytical approach. So you'll see in the upcoming lecture that how and what type of analysis is done in Routh-Hurwitz's criteria in order to approach for the conclusion of stability or instability of the system. The second is the Nyquist criterion. The third is the Bode plots. So these two criterion will be the Nyquist and Bode will be, I guess, are in the next unit, unit 4. So we'll study about these criteria of plots, and these are the graphical approach in order to conclude about the stability of any system. Now, for a system to be stable, there are certain conditions which needs to be satisfied, and they are subdivided into two parts. One is called as necessary, the other is sufficient condition. So, in fact, sufficient condition is the Routh-Hurwitz criteria. So, we are going to apply Routh-Hurwitz criteria in order to finally conclude whether the system is stable or unstable. But before applying Routh-Hurwitz criteria or assessing the sufficient condition, it is important to uh, ascertain the necessary condition pertaining to the system. So if you are going to have necessary condition of stability fulfilled, then you are going to move towards sufficient condition or Routh-Hurwitz criteria for the system. So in general, the characteristic equation 1 plus gs hs can be expressed in polynomial form as follows. So now suppose that we generalize the characteristic equation in this manner. We have a naught s to the power n plus a naught s to the power n minus 1 plus a1 s to the power n minus 2 plus up till a naught equal to 0. So sorry, there is a slight mistake here. So this should be a n. So this is a n. This is a n minus 1, a n minus 2, or rather we write this in the opposite form. Let's call this as a naught. This is a1, a2. So it will be simpler to write in this manner up till an. So we have coefficients a naught, a1, a2 up till an, which are constants associated with the equations. And then let's say this is a characteristic equation of order n. So by looking at the highest power of s that we have for this equation, we can conclude for the order of the system. And suppose that after knowing the characteristic equation, then we have necessary conditions for the system to be stable. So in order for the equation 1 should have no roots with positive real parts, or in other words, there should be no roots lying on left right half of S plane, or no poles of the transfer function lying on right half of S plane. It is necessary that the following conditions are satisfied. So there are two conditions. The first is all the coefficients of the equation 1 should have same sign. What does it mean? So if you're going to look at this particular equation, so the coefficients associated with this equation should have same sign. For example, if suppose I was given a characteristic equation of the form 5s to the power 4 plus 3s to the power 3 plus 5s square plus 1s plus 2 equal to 0. And then I have another equation 5s to the power 4 minus 3s cube plus 5s square plus s plus 2 equal to 0. So if I apply equation 1, apply this condition 1 to these two equations, so I see that the condition 1 satisfies for the first relation, but it doesn't satisfies for the second relation. Since I have a negative sign associated with this coefficient, and thus the first necessary condition is not fulfilled in the relation 2, and thus we straightforward say that the relation 2 exhibits or it portrays an unstable system. Then I have the second condition, which says that no coefficient of equation 1 can have 0 value. That is, if you have equation 1 within which, if suppose any of the coefficient within the equation is missing, is 0, then the system will not be stable. For example, let's say if I have a relation given as 5s to the power 4 plus 3s cube plus s plus 2 equal to 0, or 5s to the power 4 plus 3s cube plus 5s square plus s equal to 0. So in both these equations I have missing terms. I have a coefficient corresponding to s to the power 2 as 0, which is missing here, and then I have a coefficient an missing in the second relation. In this relation I don't have any coefficient an. So both these equations are not satisfying relation or condition 2, and thus they represent an unstable system. So it is necessary for assessing the stability of any system that both these necessary conditions are satisfied first. So we whenever we have these two equations violated, these two conditions violated, we straightforward say that the system is unstable, and we don't move towards the towards applying the sufficient condition. But in case if these two necessary conditions are fulfilled, then in that case we conclude that the system might be stable. So it's not till now necessary that the system will be stable, because these two conditions are necessary but not sufficient. So there is a third condition which we say as sufficient condition of stability, and we assess that condition, that sufficient condition, after knowing that the system under study had fulfilled the two necessary conditions. So that sufficient condition is in fact the Routh-Hurwitz criterion that we'll study in the next lecture. So written here is these two conditions are necessary to be satisfied for system to be stable, and then we have the sufficient condition that we are going to study tomorrow. And if you now have any question related to the lecture that we have taken, you can ask me.